Hey everybody, it's Mr. Carr again. Today we're looking at 3-5 day one. So you've done similar things to what we're going to do today already. We're going to be modeling, what you've done in the past is you've modeled data using polynomial functions. So we talk about modeling data, we are talking about regressions. So that's what we're focusing on today. We're only going to focus on two specific types, exponential and logarithmic. Okay, so when we go into this one, so here's our first example. The growth of a culture of bacteria is shown in the table. Use exponential regression to model the data. Then use your data model to predict how many bacteria there will be after 24 hours. So in this setup, we see we have all these values. We need to go into our graphing calculator or Desmos and do our regression. But now we're going to do it as an exponential regression. So I've already got it set up. I'm going to pull up Desmos. In graphing calculators, don't forget when you do this, you're doing the same process as before. You go to stat, edit, L1, L2. When you go to stat, calculate, there is an EXP regression. So you're going to arrow down for the stat, calculate, EXP regression. But I'm going to go ahead and show Desmos in here. And get rid of this older stuff here. So here is my, let's make that fit. Here is my bacteria after a certain amount of hours. Okay. What you type in, you see down here, it is Y1, and there's that tilde, that approximately equal to idea, A times B. I do my exponent, I'm going to put X1 in the exponent, because remember, it needs to refer back to this table where it's X1 and Y1. So when I graph that line, it looks like that. And a pretty perfect fit. In fact, it says R squared is 1, 100% of the points are on that line. Here we have our parameters, A and B. Now, one thing to mention too, you're going to want to check that box that says log mode. Okay, gives you a little bit more. It's a slightly different setting, but we want to put it into that log mode when we do this. Okay, so what we have is parameters. A is 399.57 and B is 1.1891. So I can come back here. So I don't know, bacteria, we'll just use Y. Y equals 399.17 times, or 57, 1.1891. 57 times 1.18, I forgot it again, 1891 raised to the X power. Okay, now remember, this equation, this is going to be hours. That was my X here, and that my Y is bacteria. So if I want to use this model to help predict, I'm going to just take 399.57 times 1.1891 and raise it to the 24 hours. Okay. So I could do this with my calculator. I just plug it in now, or I can go back to my graph and use like the table there. So I can go to 24 hours if I want to in this case. So personally, I'm just going to graph the line. X equals 24. And I come over here and I'm going to look at, where does these two cross? After 24 hours, it should be 25,519.39 amount of bacteria. Okay. The same thing would happen if I plugged in my calculator. So 399.57 times 1.1891 raised to the 24th power gives me the same thing. So 517. For the bacteria, that's going to be, I'm not going to use decimal numbers on that one. Okay. So because it's referring to bacteria, not like something like money, we'll just leave it as 25,517 bacteria. Okay. So that's using our exponential regression. The next one we want to do is a logarithmic one. A group of students studied a photograph for 30 seconds. Beginning one day later, a test was given each day to test their memory of the photograph. The average score for each day is shown on the table. Use a logarithmic regression to model the data. Then use your model to predict the average test score after 2 weeks. So my logarithmic one, I've got that set up in Desmos, same thing. It's going to be, so when we do our logarithmic one, we're going to use natural log for this. Okay, so when you do this in a graphing calculator, it's going to be ln, it should be like, I think he calls it ln reg for linear, or It's not a linear regression. This is a natural logarithmic regression. Okay. So I'm going to type the same thing. I'm going to model the same exact thing as I would in Desmos, as I would have in graphing calculator here. So get rid of this older stuff here. So I made a new table. That's right here. Okay. So this is my setup for that one. You see how it has that kind of slight curve going downwards on that one. So with this, here's what the natural logarithmic regression looks like. So in this case now, keep in mind, I used y2 and x2 because my new table here was x2, y2. If you just always put it in terms of x1, y1, that's fine. Just make sure that the table here matches your equation down here. So when I look at this one, again, make sure that log mode is checked. We get our parameters a and b. So a is equal to 73.0916, and b is equal to negative 7.3126. Okay, look at where a and b go. A is going to be in the front, like this. B is multiplied by the natural logarithm. So that's my setup when I do this one. Okay, so write those down here, 73.0916. Plus, well, minus, I guess, 7.3126. 7.3126 natural log of x. Okay, you would get the same exact thing using your graphing calculators if that's the method you used. So now that I have this, I want to use it to predict 2 weeks. Well, remember, x was number of days. So that means in this case, I'm going to use x equals 14. So y equals 73.0916 minus 7.3126 times the natural log of 14. So the score percentage based on this prediction, so 73.0916 minus 7.3126 times the natural log of 14. The score should be about a 53 point. Since my scores are only 1 decimal point, I'll do the same thing. So 53.8% is what we would expect from that one. Okay. And again, you can actually get that from doing this here. The score after 2 weeks will be at 14, 53.8 right there. Okay. And I believe that is going to be it. Yep, that is it for today. So again, we're looking at exponential and logarithmic regressions. So most of these questions, they'll tell you if you're going to do exponential or logarithmic. We're going to look over one more in the next video, as well as choosing your own based on what the data looks like. All right, that's it for today. Take care, everybody.